Dear students, our today's lesson is a very important because it will help us to understand our previously conducted experiment, and it will also help us to plan and design our next and the final experiment. More importantly, that this today's lecture will also help us to prepare our project reports to major parts. Number one is the results, and the second is the discussions. So please go through this lesson very carefully and prepare your notes that will be the part of your project reports, results, and discussions sections. Dear students, today we will discuss our previously performed experiment on electromagnetic induction. And we will also see that this experiment was mainly qualitative experiment. And then at the end, we will plan a new experiment that must be a quantitative experiment, meaning that where we would be able to do the analysis with the input voltage, output voltage, that how much induction is happening and what will be the efficiency of this induction. That what is also lead us to understand how to calculate the efficiency of a transformer. So before going to start the discussions, let's have a look on our previous experiment that what we did. Before that, let me explain you the circuit that what we actually connected here. Here, what we do have, we have a primary coil, and this primary coil is connected with the signal generator. So here we have a signal generator. So this signal generator can actually provide us the input voltage like a sinusoidal wave or a sawtooth wave or a square wave, and we can also control the frequency of the input signal. And this is connected with our this primary coil over here. And this primary coil, you can see that it is like a solenoid. And then the second coil, which is our secondary coil over here, this coil is a circular coil. And in the primary coil, we have about 200 number of turns. And in the secondary coil, we have about 300 number of turns. And you can also see that the diameter of both of these coils are actually different. So secondary coil has almost more than a double the diameter compared to the primary coil. And then this primary coil is also connected with our this oscilloscope, and this oscilloscope's first, you can say the channel number one. So you can see here that this yellow wave, it is actually our primary voltage signal. And this bluish channel, which is the channel number two, it is connected with our secondary coil. So secondary coil is directly connected with the channel number two. So this belongs to our secondary voltage. So now, once again, the primary coil is connected with the signal generator, where we are actually giving the input signal, which looks like this yellow signal, and it is a sinusoidal signal with a certain frequency. Secondary coil is connected with the channel number two, which is also having this sinusoidal output. So let's have a look at what happens here in this experiment. So you see, when we move this coil closer to the primary, then secondary coil get the induction. So this induction, first of all, is not because of the movement. Because of the movement, you can see the signal is actually getting bigger or smaller in the secondary, where the signal of the primary is constant here. So now let's investigate or discuss this experiment, that what is going on in this experiment. So here we have our primary coil. So in the primary coil, if you look at what we have our input signal, and you can say that here we are providing the input voltage, and this voltage we can see that it's like this cosine function. And of course, this voltage is providing the current, and this our primary voltage is producing the magnetic field, and the magnetic field of a coil can be calculated. So magnetic field of a coil is given by the following formula, and that is B is equal to mu naught N I divided by 2R. Here, color. So here, what the mu naught is the permeability of the free space here, and its value is 4 pi into 10 raised to power minus 7 Tesla meter per ampere. So this is the permeability of free space. And what I is? I is our input current. R is radius, and N the total number of turns. Total number of turns. And here I would also like to discuss one more formula of the induced magnetic field, and that is in case of a solenoid, because our primary coil here in this experiment is just like a solenoid. Then our produced magnetic field will be B is equal to mu naught permeability of free space, small n times I. Again, I is the current. And here, this small n is the number of turns per unit length. Number of turns per unit length. So then you can say that in this experiment, this formula is actually for producing the magnetic field. But if you will have your primary coil like a circular coil as we have as a secondary coil, then you will use this first formula to calculate the magnetic field. Now, what is happening here? Of course, electromagnetic induction is happening. Then this will follow the Faraday's law. What Faraday's law is? It is following. The Faraday's law actually tells us that the induced EMF is proportional to negative a rate of change of magnetic flux. So what the magnetic flux is? Magnetic flux is the magnetic flux density times the cross-sectional area is the cross-sectional area. So A is our cross-sectional area of the coil. So you can also see that the secondary coil has a bigger cross-sectional area compared to our primary coil. Now here, this negative sign, we know that it is because of the Lenz's law. So what Lenz's law tells us that this negative sign is because of the Lenz's law. What Lenz's law tells us that this induced EMF opposes the magnetic flux change. What? The induced EMF, induced of course, induced EMF opposes the flux change. And one more important thing is that this flux is the flux which is linked with our secondary coil. So this is simple mathematics to understand our this experiment. So what is going on that we applied our signal, and that signal is our time dependent signal. And this time dependent signal has a non-zero time derivative. So definitely there is induction, and we are getting the EMF, induced EMF in our secondary coil. Now let's have a very careful look on our this input and output signals. So for that, we write a little more mathematics of our these input and output signal. Then we would see that either these signals looks realistic signals or they have some issue or the problem. Okay, now let's have a look at our input and output signal. The input signal here, you can see that it starts from the max value. So it is following the cosine angle. So it is like a cos theta. And what about the output signal? Here, output signal starts from a negative max value because this is the principal axis. So then it is following negative cos of theta. Now we looked at the Faraday's law, that the Faraday's law has the time derivative of input signal that will give us the output signal. So apparently, it looks that if the input signal is cosine, that output should be the sine. What this signal is exactly right, why it is so. So let's give a little bit, you can say the insight thinking. So let's have a look at this, that we have our primary voltage, which is like V naught into cos omega t. And here, omega is the angular frequency, which is 2 pi, the linear frequency f. In case of the coils, and this coil is also like inductor here. So then this inductive effect actually lags the voltage compared to the current by a 90-degree. And this voltage can be written as the inductance L and the time derivative of current. Now we can rearrange this equation and also put the value of the primary voltage. Then we can see that it is equal to the derivative of the current is equal to V naught over the inductance times the cosine cos omega t times the dt. Now we can integrate this equation. So our simple answer will be that the current is equal to V naught divided by the L times the omega because of the integration of the cosine. So answer is the sin omega t. Now you see that our current that we are getting here in our primary coil, it is the function of the sin omega t. And we know that the magnetic field which will be produced by this current must be equal to the B is equal to mu naught, which is a constant, and the number of turns per unit length is also constant, times the current. So this current will be I naught times sin omega t. So here I am putting these constants like the I naught. Now we can take the time derivative of this magnetic field. So dB over dt is equal to our this mu naught n I naught omega times cos omega t. Now, by the Faraday's law, our induced EMF will be equal proportional. Let's do in a very simple mathematics is equal to the dP over dt. Now we can see that these are the constants here. So we can simply find that our induced EMF will be proportional to the negative cos omega t. Now you can see that our input signal is the cos omega t and output signal is negative cos omega t. This is what exactly we see here. So now we can do a little bit more discussion on our this experiment. Here, you can also raise another question that what is happening that we do have two different coils. We have a primary coil, we have a secondary coil, and there is an induction, and we have a time-dependent input signal. So we are getting the induction through this Faraday's law. And this is also a simple, you could say, the configuration of a transformer. So it means that we can do a quantitative analysis of our input and output signals using the transformer equation. So what is the transformer equation is which relate the input and output signals like the voltage in the primary coil divided by the voltage in secondary coil is equal to number of turns in the primary coil divided by the number of turns in the secondary coil. So by using this relation, you can also investigate that either you are having the step up transformer configuration or step down configuration. And here you can very easily see that what would happen that if your number of turns in primary are greater than the number of turns in secondary, then we will have a step down transformer. So step down transformer means that our voltage will decrease at the output. So then if we have this, the number of turns in the primary are less than the number of turns in secondary, then we will have a step up transformer. So meaning that the output signal will be bigger compared to our input signal. So here you actually can also do this quantitative analysis of your experiment. You can try the different coils that have a different number of turns. But the most important and the interesting experiment here that I wish that if you can do is the following, that now if you see that what is happening, that we are moving our coil away and then the output signal is decreasing. What you can do the following. You can fix your number of turns of the primary and the secondary coil and also provide a fixed signal from the signal generator and then investigate the output voltage as a function of the distance of the secondary coil. So then at the end, what we would have the following graph. So for example, this is our y-axis, this is our x-axis, and here it is the our y-axis, and that will be our secondary voltage in volts, and x-axis that will be our distance between the coils and in centimeters. So how would you measure the distance? So the distance here, you should have from your primary coil to your secondary coil, this distance between. But we have this solenoid. What you can do, you can take the, you can say the distance from the center of such a coil. But I should suggest you that you should use the circular coils, the coil which is like this secondary coil. And then here, what we would have our, the input voltage that is the constant, though you mentioned that number, and then number of the turns of the primary coil, that is constant, and then number of turns in the secondary, that is also constant. So we will mention these numbers. Then we will plot our results, and the result may look like this. What you need to see that what is happening in your experiments. So here, this is actually giving you the opportunity to investigate the output voltage as a function of the distance of the coil using a different configuration of your input voltage and the number of turns of the primary and secondary. And one more important thing which we are missing, that is the frequency of our input signal, that you can also keep it constant. For example, we have like 100 hertz. It is up to you. You can also change it, and you can have develop many different graphs over here. And then now at the end, I would also ask you a question that what you people must investigate, because this configuration of our experiment is just a very simple configuration of a transformer. So in this case, what you can also do, you can also investigate the efficiency of your transformer. So how do we uh, efficiency, we investigate the efficiency. So efficiency is equal to our, you can say the output output power divided by the input power. Input power. So power is, our output will be secondary current times secondary voltage divided by the primary current times the primary voltage. Now, if we need to investigate our this experiment quantitatively, meaning that we need to have the numbers to plot our experiment, to investigate also the efficiency of our this transformer configuration, then we should have a different you can say the setup. Now let's discuss that how this setup must look like. Okay, now let's discuss our new setup for our uh, better next experiment. So for this, what we have our primary coil, and this is the primary coil. And this primary coil is connected with the signal generator, which is providing us the AC voltage. And of course, we can change the frequency there. So this is the signal generator. And then we have nearby our secondary coil, and that secondary coil is over here. Now, this is the primary coil. This is a secondary coil. What we need to know? We need to know the voltage. So the voltage will be provided by the oscilloscope. And this oscilloscope is providing us the input signal and output signal. But remember that this oscilloscope can actually provide us the peak voltage. But for the calculations, we always use the RMS values. So the relation between the peak voltage and the RMS voltage is the following, that the peak voltage is equal to the square root of 2 times the VRMS. When we use the multimeter, then we measure the VRMS. So it means what we can do, we can also connect our one of the voltmeters parallel to our primary coil, and similarly one voltmeter parallel to our secondary coil. So you can also test this formula, that the voltage which you will record using your multimeter, that will be VRMS, and the voltage that you will actually check through this oscilloscope, that will be the peak voltage. Now, here, these two things are over there. So we have this Vs that would be over here, and Vp that we will get over here. Number of turns are, of course, we have our these known numbers when we will be using our certain coils, and the distance that we will measure. The second thing is that now we are going to connect both of these coils with one oscilloscope that will have two channels. So channel number one, you can connect it, for example, with the primary, and the channel number two, you can connect it with the secondary. It's up to you. So now this is going to be connected over here in the oscilloscope, and similarly, our this primary will also be connected with the oscilloscope, and we will see some signal over here. Of course, there will be two signals on this oscilloscope. So this will be our new setup. Then one question is that if we want to investigate the efficiency of this simple transformer configuration, then we also need to measure the current in these two coils. So for that, we need to put the ammeters in series over here and over here. So it means you need 4 multimeters, one signal generator, two coils, and one oscilloscope to perform your this experiment. And then you need to record these all values in a very careful way. So I would suggest that you actually prepare a table, and in this table, what we would have mainly, that we actually need to have the distance, and we need to have our the you could say the Vs, the secondary coil. So of course, then our this primary voltage will be constant. Then the number of turns in the primary and the number of turns in the secondary. So you can have this table. So you can also make it even a simple table where you will have only two columns, these distance and the output voltage. And then on in the caption, you can give these constant values of your number of turns and input voltage. And of course, the frequency as well. Do not forget the frequency. So now, if you will have any question, so you can actually write to us. So we will provide you the answers. Thank you very much for your time. Hope you will enjoy your next experiments. Dear students, our today's lesson is a very important because it will help us to understand our previously conducted experiment, and it will also help us to plan and design our next and the final experiment. More importantly, that this today's lecture will also help us to prepare our project reports to major parts. Number one is the results, and the second is the discussions. So please go through this lesson very carefully and prepare your notes. That will be the part of your project reports, results, and discussions sections.